I've kept the diagram from our last example up here, as well as the formula that we had figured out for figuring out the partial of z with respect to theta. So we had z was a function of x and y. X and y were both functions of r and theta, so here were our usual conversion formulas. And here, although the book doesn't use this notation, if I wanted to, I could view this as one function, where the input is r theta, and the output is xy. So that would be a vector-valued function. The output is multidimensional, because it's a point in two space, it's xy. And the input is also multidimensional, because it's r and theta. Just wanted to point out that when I did this, we got a sum of products. We're pretty much always going to get a sum of products. But a sum of products I can always interpret as a dot product. This would be the dot product of partial z, partial x, partial z, partial y. Those are the partials from the top part of my diagram, dotted with partial x, partial theta, partial y, partial theta. Those are the derivatives from the bottom part of my diagram. Okay. Well, this has a name. That's the gradient of f. Remember, f was the function that was giving us z as a function of x and y. And this also has a name. If I were to give a single name to this function, whose components are the x function and the y function, if I were to call that whole thing r, this is just the partial of r with respect to theta. So anytime we are using the chain rule like this, we will be able to express our result as a dot product of two derivatives, sometimes a full derivative, sometimes a partial derivative, but we will be able to do that. Now, I think for our purposes, drawing the diagram to see a picture of all of the paths that are connecting one variable to another is the simplest way. And in this semester, we will occasionally see functions with a multidimensional input and a multidimensional output. As we're working with the chain rule, this intermediate function did have a multidimensional input and a multidimensional output, but we're always looking at diagrams where we've got just a single number as the output. We're only looking at situations where the end result is spitting out a one-dimensional output, or just a number. There are certainly functions where you can plug in a point in 3 space and get out a point in 2 space. Now, we're not working with those very often this semester. Turns out, if you did that, the derivative, rather than being a vector, like the gradient, would actually be a matrix. It would be the matrix consisting of all of the partial derivatives. And it's very interesting, but you can work with partial derivatives by thinking of it all in terms of matrix multiplication. Now, I mention this because some of you have taken or are taking linear algebra or might be familiar with matrix multiplication. This is an optional thing. There is a handout posted on Canvas that gives you a fuller picture of the chain rule and includes functions that have both a multidimensional input and a multidimensional output that allows for the possibility of the derivative actually being a matrix. And it will incorporate all of the rules that we've seen here, which end up with derivatives or partial derivatives simply being a dot product, but it will also talk about the full derivatives of a function that, say, has a 3-dimensional input and a 2-dimensional output. That handout is available on Canvas. If you are interested in it, you're more than welcome to read it, and I'm certainly happy to answer questions about it. So I wanted you to know that it's out there. You won't be responsible for that interpretation of things, but I think it is neat to see that this diagram is always leading to some sort of a dot product. And just to, even if that's all you see, is just get a glimmer of that, just sort of see there's a bigger picture out there that involves dot products and multiplication of matrices for finding derivatives anytime we have a function composition.